A city built on water faces a mathematical problem. The tide is rising faster than the foundations can be raised, and every conventional seawall would block the port that keeps the economy alive. By 2003, Venice was flooding more than 60 times a year, and engineers had to design a barrier that could stop a 2-meter storm surge without building a single, permanent wall across the lagoon. Venice sits inside a shallow lagoon, connected to the Adriatic Sea by 3 natural inlets. For centuries, the city survived occasional high tides called acqua alta, but subsidence from groundwater extraction and global sea level rise changed the equation. Between 1900 and 2000, the relative sea level at Venice rose by roughly 23 centimeters, and the frequency of flooding multiplied. In November 1966, a catastrophic tide submerged the city under nearly 2 meters of water, destroying art, displacing residents, and forcing the Italian government to confront a question no one had solved. How do you defend a lagoon city without killing the tidal exchange that prevents it from becoming a stagnant swamp? The project that emerged was called MOSE, an acronym for Modulo Sperimentale Elettromeccanico, and a deliberate reference to Moses parting the Red Sea. The design called for rows of hollow steel gates buried in concrete foundations on the seabed at each of the 3 lagoon inlets. Under normal conditions, the gates would rest flat and invisible, filled with seawater. When a dangerous tide was forecast, compressed air would be pumped into the chambers, forcing the water out and rotating each gate upward on hinges until the barriers formed a temporary wall. Ships would stop, the tide would be held outside, and once the surge passed, the gates would flood again and disappear. On paper, the concept was reversible and elegant. In practice, it required 78 individual barriers, each weighing up to 300 tons, to be installed across inlet channels as deep as 20 meters. The gates had to withstand wave forces, saltwater corrosion, ship traffic vibration, and sediment movement, then reliably surface and reseal thousands of times over a 50-year lifespan. Construction began in 2003 with a budget of roughly 1.6 billion euros and an expected completion date of 2011. The Italian government framed MOSE as a technical solution that would preserve both the historic city and the lagoon's economic function, avoiding the political cost of retreat or the ecological damage of a permanent closure. The first engineering compromise appeared in the hinge design. Each gate rotates on massive steel hinges anchored into prefabricated concrete caissons, which were cast on shore, floated to position, and sunk onto leveled seabed. Surveyors discovered that sediment compaction and tidal scour made it nearly impossible to guarantee a perfectly level foundation across the inlet width. Even a small angular error would cause the gates to misalign when raised, leaving gaps that would allow water to pour through under pressure. Engineers responded by designing self-leveling hinge assemblies with hydraulic adjustment mechanisms, adding mechanical complexity and maintenance liability to every connection point. The solution worked, but it meant that every gate now depended on active systems rather than passive geometry, multiplying the number of components that could fail during an emergency deployment. Corrosion became the second unresolved variable. The gates spend most of their operational life submerged in seawater, exposed to salt, biological fouling, and galvanic reactions between dissimilar metals. Original specifications called for stainless steel and protective coatings, but as construction progressed, inspectors found welds that did not meet tolerances and joints where coatings had been applied unevenly. In 2013, a corruption investigation revealed that contractors had substituted cheaper materials, falsified inspection records, and received approval for substandard work. More than 30 people were arrested, including the project's chief engineer and the mayor of Venice, and the entire system had to be audited gate by gate. The investigation delayed completion by years and forced engineers to retrofit barriers that had already been installed, pulling them from the seabed to replace compromised components. The cost and timeline spiraled. By 2020, MOSE had consumed roughly 5.5 billion euros, more than 3 times the original estimate, and construction had stretched across 17 years. Critics argued that the money could have funded less intrusive solutions, raised walkways, building-level flood barriers, or managed retreat from the lowest-lying districts. Environmental scientists warned that closing the lagoon inlets would reduce tidal flushing, trapping pollutants and warm water that fuel algae blooms and threaten the ecosystem that fishing and aquaculture depend on. Supporters countered that no combination of local defenses could protect the entire historic city during a major storm surge, and that partial measures would only delay the choice between defending Venice or abandoning it. The debate intensified as construction costs climbed, but by the time the financial scale became clear, the project was too far advanced to cancel without losing the entire investment. In October 2020, MOSE was activated for the first time during an actual acqua alta event. All 78 gates rose. The tide was held at the inlets, and the water level inside the lagoon stayed below the flooding threshold. For the first time in centuries, Piazza San Marco remained dry during a forecast high tide. The system has since been deployed more than 100 times, and it has prevented flooding in every activation. Each deployment requires coordinated timing across all 3 inlets, constant monitoring of weather forecasts, and manual inspection of the gates after they retract to check for damage or fouling. The operational routine has become more efficient with repetition, but it remains a high-stakes procedure that depends on human judgment and mechanical reliability in equal measure. But operational success has not resolved the underlying contradictions. Each deployment costs an estimated 30,000 euros in energy and labor, and the gates require continuous maintenance to address wear, fouling, and corrosion. The Italian government has committed to an annual operating budget, but long-term funding depends on political will and economic stability that cannot be guaranteed over decades. Maintenance crews must inspect, clean, and repair gates on a rotating schedule, pulling them from service for weeks at a time and reducing the system's total capacity during vulnerable periods. Sea level rise projections suggest that by mid-century, MOSE may need to close so frequently that tidal exchange is chronically restricted, transforming the lagoon's ecology in ways that are difficult to reverse. Engineers are already studying whether the barriers can be modified, supplemented, or replaced, but no consensus solution exists. Some proposals call for raising the gate's maximum height, others for building secondary barriers inside the lagoon, and still others for integrating MOSE into a broader, managed retreat strategy that accepts partial flooding of the lowest districts. MOSE works because it turned a permanent problem into a reversible intervention. The gates prove that massive movable structures can be reliably operated in marine environments, that corruption and material substitution can be discovered and corrected without scrapping the entire project, and that a city does not have to choose between preservation and functionality if the engineering is patient enough. But the system also proves that defending against sea level rise is not a one-time construction victory. It is a commitment to operate, maintain, and eventually reimagine infrastructure as the baseline conditions continue to shift. Venice is not saved. It is continuously defended, and the cost of that defense will be paid every single year for as long as the city remains inhabited. The gates bought time, but they did not stop the clock, and the next generation of engineers will inherit both the working system and the unresolved question of what happens when even MOSE is no longer enough. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.